Hello, and welcome to this discussion of energy and work for reactor fluid mechanics. So, we've already defined a number of basic terms, so right now we're going to start adding some additional terms. We're going to start by talking about the specific heat capacity, which is often shortened to just be specific heat. This tells us how much energy a particular amount of something can absorb when it changes temperature. So, for instance, CV is the change in specific internal energy per temperature. So if we have 1 kilogram of a substance and it changes temperature by 1 degree Celsius, CV tells us the total energy change for that 1 kilogram when it changes temperature by 1 degree Celsius. CP tells us the change in enthalpy, which we'll get to a little bit later. So internal energy then is our capital U. It's the energy contained within the system. So its units are energy, joules. And it can be broken up into several different categories. The first one is sensible heat. Sensible heat is associated with temperature. Okay, so sensible heat does not change during phase change, during melting or boiling or condensation and so on. But it does change whenever there's a change in temperature. Boiling and condensation and so on are associated with latent heat, which is associated with the attraction between molecules. We also can talk about chemical energy. Chemical energy is associated with attractions between atoms, and so for instance we can go through a combustion reaction which converts chemical energy into thermal energy, in sensible or latent heat. And we also have nuclear energy, which is associated with the binding energy between the particles in the nucleus. And through processes like nuclear fission, we can convert that energy into thermal energy, sensible or latent heat. Now, we're mostly going to be concerned with sensible heat during this class and the next couple of classes in this series, because the change in fluid properties is going to be important for calculating work and so on. Now, the values for the internal energy, the specific internal energy, are tabulated. You can look them up in tables in the back of the textbook or online and so on. So, we also need to define some additional work and energy behaviors. The first is kinetic energy. So kinetic energy is associated with the macroscopic motion of the fluid, or the flow of the fluid. And potential energy is associated with work that's done in an external field, like a gravity field. So for instance, when the fluid moves up, it gains potential energy, and when the fluid moves down, it loses gravitational potential energy. And we add these three things up to make the total energy. So the total energy is the sum of internal, kinetic, and potential energy. This energy can be transferred, moved from one location or one fluid to another by either work or by heat transfer. So work is a transfer of energy due to the motion of the boundary of the system. So work is transfer of energy due to motion. It is not a property, but it is associated with some kind of a process. And the amount of work done depends on the path you take to go from one point to another in the process. Then we could talk about power. Power is just work done per unit time. So we can divide our work up into a few different categories. The first one is gravitational work. Gravitational work is basically the work done to lift an object, to change its potential energy. So the work done by gravity is mg times the change in height. Acceleration work is the work required to accelerate an object, to change its kinetic energy. And so acceleration work is just the change in the kinetic energy from point 1 to point 2. And then the pressure work is done when a fluid expands, right? There's a pressure force that causes the fluid to expand, so you have a force that moves through a distance and does work. So the plot of how the pressure changes with the volume of a fluid results in a PV diagram, like the one shown here on the slide. And the work then is the area under that curve. And as I said earlier, that work done depends on the path. Electric work can also be done in a system by electrons that move across the system boundary. If they enter the system with high voltage and leave with low voltage, then you have voltage times current and you have power. We can also do spring work to compress or release a spring. Now it's important to define the sign convention for work. Work done by a system is positive. It gives us energy to do something else. Work done on a system is negative. What does this mean? Positive work actually reduces the energy of the system, and negative work increases the energy of the system. Now, work is going to be the focus of power plant systems, but we are going to talk about it a little bit through this course and through heat transfer as well. We also need to talk a little bit about heat transfer. So, heat transfer is also an exchange or motion of energy. However, heat transfer is due to changes in temperature rather than motion. So when one object is at a higher temperature than another object, heat will move from the hotter object into the cooler one. Again, heat transfer is not a property, but it is a process, and just like work, it depends on the path you take to get from one point to another. Now, we can also talk about power as the rate of heat transfer, but the rate of heat transfer is in terms of it's Q with a dot, whereas power due to work is W with a dot. Now, heat transfer occurs through three major processes. The first is conduction. Conduction is heat transfer due to the interactions of molecules in a system that's stationary, a solid or a stationary fluid, where the molecules basically bump into each other and transfer their energy that way. Convection is the next one, and that's heat transfer between a surface, like a solid, and a moving fluid. And for convection to occur, you need to have two things. The first is conduction from the surface into the fluid, and the second is advection, where you have the fluid carrying energy away due to its bulk motion. The last form of heat transfer is radiation. This is thermal radiation, not nuclear radiation. And it basically accounts for the energy emitted by all objects as electromagnetic waves. You can actually measure this. You can see it in infrared cameras and so on, where they measure the amount of infrared radiation given off from an object in order to determine its temperature. So heat transfer is going to be the next class in this series, reactor heat transfer. But again, I want to mention the sign convention for heat transfer. It's the opposite of work. So heat transfer into a system is positive and increases the system energy, whereas heat transfer from a system is negative and it reduces the system energy. We'll see the reason for this sign convention in just a minute. So, in order to do that, we need to talk about the first law of thermodynamics. Now, we start with the Reynolds transport theorem, and then we use the energy. So we have the specific energy. So we have the internal kinetic and potential energies together. Now, in general, the kinetic and the potential energies are much smaller than the internal energy. So in many cases, we can neglect them and just say that E equals U. As we go through the rest of the slide, we're going to leave E until the very end. But just so you know that in most cases, we can make that approximation. So if we substitute this, we basically end up with the change in total energy is equal to the heat in minus the heat out, plus the heat that's generated in the system, plus the work done on the system minus the work done by the system. And we can simplify all of the heat and work terms to just say the change in energy is equal to the total change in thermal energy and the total change in work. So total work done. And again, note the sign convention. Heat transfer into the system is positive and therefore increases the energy of the system. Work done on the system is negative. Then you have two negatives, so work done on the system increases the energy of the system. So this is why we have the sign convention set up the way it is. Now, if we expand the work, we can look at, so now we end up with the first law of thermodynamics by expanding the substantial derivative. Now, we can further simplify this by expanding the work. And so we have a pressure work term, we have a shaft work term, which is done by a rotating element, so for instance like a pump or a fan. And then we have other work, which is just kind of a catch-all category in case we have some other element doing work on our system. So we're going to move the pressure work by using the definition of work as the integral of PdV over to the left-hand side. And we end up with this total energy plus P over rho in our flow term, the mass flow term. So we're going to introduce at this point the specific enthalpy. So the specific enthalpy is just the internal energy plus pressure over rho. Where internal energy measures the motion or the energy associated with the motions due to molecules, enthalpy measures that energy plus the potential of the fluid to do work by expanding. So this is the form of the energy equation we're going to start with, and then we can look at applying some assumptions. So we're going to look at some of those assumptions and start looking at the flow term, right? So the flow term has rho, density times velocity times area times enthalpy. Well, density times velocity times area is mass flow rate. So we can actually rewrite that particular term just to be the sum of all the mass flow rates in and out times the enthalpies at that point. So if we have a steady state system, then the time derivative goes away, and we have the total change in the energy of the flow, right? The total energy leaving minus the total energy in associated with the flow is equal to the heat added minus the net work. So, for instance, if you have the picture here, we can see here's our energy in, and here's our energy out, and here's our shaft work done, and here's our heat transfer leaving. So we can add up all of these things. So what that means is, if we know the energy in, and we know the shaft work, and we know the heat transfer, we can figure out the enthalpy of the fluid that's leaving this object or this system. We can also look at a control mass. So for a control mass, there's nothing allowed to cross the system boundaries. At least no mass is allowed to cross the system boundaries. So that means that the flow term is zero. The mass flow rates are all zero. And so we can simplify that to the change in internal energy with time, or du dt, is the sum of the heat transfer and all the work done, the net work. So that wraps up our discussion on the first law of thermodynamics. We will come back to this a little bit more when we get into heat transfer next semester, but for now, this is where we'll leave it.